Today, students, welcome to our class again. Today, we're going to talk about logarithmic functions. But before that, let's have a review first regarding our previous topics. Okay, let's have the following definitions first. One-to-one function is the function is one-to-one if no two ordered pairs in the function have the same second component and different first components. Next, a relation is a set of ordered pairs. The domain of a relation is the set of first coordinates. The range is the set of second coordinates. Again, the domain is the x, or the input, or the independent variable. The range is the y, or the output, or the dependent variable. Next is function. Function is a relation in which each element of the domain corresponds to exactly one element of the range. Remember, all functions are relation, but not all relations are function. Okay, let's have the steps in finding the inverse function of the one-to-one function now. First, find the domain of f and verify if it is one-to-one. If it is not one-to-one, then stop. It means the inverse does not exist. Next, solve the equation y equals f of x for x. Next, interchange x and y in the equation in step 2. This expresses the inverse of f or the f negative 1 as a function of x. The last is find the domain of f negative 1. And note that the domain of f negative 1 of b the same as the range. Okay, let's have the following definition about logarithmic and exponential. The logarithm of y to the base b is equal to x if and only if b to the power of x is equal to y. For b is greater than 0 and b is not equal to 1. A logarithm is an exponent which b must have to produce y. In either equation, b is called base and must be a positive number not equal to 1. And the equations x is equal to logarithm of y to the base b and y is equal to b to the power of x are equivalent, or they are the same. The first equation is in logarithmic form. So the symbol there, log, that means logarithm. And the second is in exponential form. They are equivalent. Here, the logarithmic function to the base a, where a is greater than 0 and a is not equal to 1, is defined by. So here, we use a variable a. So y is equal to logarithm of x to the base a if and only if x is equal to a to the power of y. So the first one is logarithmic form and the second is exponential form. Remember, they are equivalent. So when you convert an exponential to logarithmic form, notice that the exponent in the exponential becomes what the logarithm is equal to. Example here, convert to logarithmic form. We have 16 is equal to 4 squared because 4 times 4 is 16. And the base here is 4, the exponent is 2. And we will convert that to logarithmic form. We have logarithm of 16 to the base 4 is equal to 2. So the base here in the exponential form is still the base here in logarithmic form. The small number, that is the subscript in the symbol log, which means logarithm. And the exponent here 2 will be the logarithm here in logarithmic form. And we'll do the reverse. We will convert the following to exponential form. So we have the logarithm of 1a to the base 2 is equal to negative 3. So our base here is 2 and our logarithm is negative 3. So if we will make that or convert that to exponential form, still the same. The base is 2, and the logarithm there, the negative 3, will be the exponent here in the exponential form. So 2 to the power of negative 3 is equal to 1/8. Okay, some examples here. You write each exponential form in logarithmic form. Letter A. 3 squared is equal to x. The base here is 3, the exponent is 2. Remember, exponents are the logarithm. So that means the logarithm of x to the base 3 is equal to 2. So the exponent there in exponential form, which is 2, becomes the logarithm here in logarithmic form. Letter B. 8 to 1 is equal to 3 to the power of x, means the logarithm of 8 to 1 to the base 3 is equal to x. Yes, we know that in the exponential form, the base is 3 and the exponent is x. Still in logarithmic form, the base is 3 and the exponent x becomes the logarithm. Letter C. 10 to the power of negative 2 is equal to 0.01. Means logarithm of 0.01 to the base 10 is equal to negative 2. The same process, the base still the base at the logarithmic form, and the exponent here in exponential form becomes the logarithm here in logarithmic form. Last, e to the power of y is equal to 9, means the logarithm of 9 to the base e is equal to y. Okay. Remember, exponents are logarithms. The base remains the same. So do not change the base, and exponents are logarithms. So here, write each logarithmic equation in exponential form. So the first one is logarithm of x to the base 5 is equal to 4. So the base here is 5 and the logarithm here is 4. And if we will convert that to exponential form, still the base is 5 and the exponent will be 4 is equal to x. Next, logarithm of 64 to the base 2 is equal to 6. Still the base is 2 here and the logarithm is 6. Remember, exponents are logarithms. So we have 2 to the power of 6 is equal to 64. Next, the logarithm of m to the base a is equal to 7. Means a to the power of 7 is equal to m. And the last is x is equal to logarithm of b to the base c. Means c to the power of x is equal to t. So those are examples on how to convert exponential to logarithmic forms or vice versa. Okay. Again, logarithms is equal to exponents. With this in mind, we can answer questions about the logarithm. First, logarithm of 16 to the base 2 is equal to 4. This is asking for an exponent. What exponent do you put in the base of 2 to get 16? So that's the meaning. So 2 to what is 16? So 2 to the power of 4 is 16. Next is logarithm of 1 over 9 to the base 3 is equal to negative 2. What exponent do you put in the base of 3 to get 1/9? So hence, we have to think negative since 1/9 is fraction. So we have 3 to the power of negative 2 is equal to 1/9. And here, logarithm of 1 to the base 4 is equal to 0. So what exponent do you put in the base of 4 to get 1? So we have 4 to the power of 0 is equal to 1. We have the logarithm of the square root of, we have the square root of 3 to the base 3 is equal to 1/2. So when working with logarithms, you will write any radicals as rational exponents, since radical can be converted to rational. That exponent we put in the base of 3 to get 3 to the 1/2. Hint here is the rational. So we have 3 to the power of 1/2 is equal to the square root of 3. Okay, we have example 1. We will solve for x. The x here is the missing number. So we have logarithm of x to base 6 is equal to 2. So the solution here is we will write the problem in exponential form. So here, the base is 6 and the logarithm is 2. Remember, exponents are logarithms. So if we will convert that to exponential form, it's very easy. So we have 6 squared is equal to x. And 6 squared is 36 because 6 times 6 is 36. So the missing x here, the known number here, the known x here is 36. Example 2. Solve for y. The logarithm of 1 over 25 to the base 5 is equal to y. So we will write again the problem in exponential form. So we have the base is 5 and the logarithm will be the exponent because logarithms are exponents. So 5 to the power of y is equal to 1 over 25. Since 1 over 25 can be written as exponential, but the exponent is negative. So we will make them like bases. So we have 5 to the power of y is equal to 5 to the power of negative 2. So y is equal to negative 2. So the logarithm there is negative 2. Next example 3. Evaluate logarithm of 27 to the base 3. Or what is the logarithm of 27 to the base 3? So try setting this up like this. Logarithm of 27 to the base 3 is equal to y. So we don't know what is the logarithm, so we will use variable and then we will write it in exponential form. As we know that we will not change the base and exponents are logarithms. So we have 3 to the power of y is equal to 27. And 27 can be written as exponential to the base 3. So 3 to the power of y is equal to 3 cubed because 3 times 3 times 3 is equivalent to 27. So we have y is equal to 3 since they have the same base. Now we can extract their exponents. Therefore, the logarithm of 27 to the base 3 is equal to 3. Example number 4. Evaluate logarithm of 7 squared to the base 10. Now we will write the problem with variables. So we will equate. So logarithm of 7 squared to the base 7 is equal to y. We don't know what is y there. That's the variable or that's the unknown number that we're going to find. So again, this is the base 7 and the logarithm there is y and that will be the exponent of 7. So 7 to the power of y is equal to 7 squared. Now take out of the logarithmic form and write it in exponential form. And since they're the same bases, just take out their exponents. So y is equal to 2. Therefore, the logarithm of 7 squared to the base 7 is equal to 2. Example 5. Evaluate 4 to the power of logarithm of 16 to the base 4. So first we write the problem variable. 4 to the power of logarithm of 16 to the base 4 is equal to y. Now take out of the exponential form and write it in logarithmic form. Since that is exponential, so we will write it in logarithmic form. So logarithm of y to the base 4 is equal to logarithm of 16 to the base 4. Since the base there is 4 and the exponent is logarithm of 16 to the base 4, so that will become the logarithm if we will rewrite that in logarithmic form. Therefore, y is equal to 16. Finally, we want to take a look at the property of equality for logarithmic functions. Suppose b is greater than 0 and b is not equal to 1, then logarithm of x sub 1 to base b is equal to logarithm of x sub 2 to base b, if and only if x sub 1 is equal to x sub 2. So basically, with logarithmic functions, if the bases match on both sides of equal sign, then simply set the arguments equal. Okay, example 1. Solve. Logarithm of 4x plus 10 to the base 3 is equal to logarithm of x plus 1 to the base 3. Since the bases are both 3, we simply set the arguments equal. So we have 4x plus 10 is equal to x plus 1. Before combining like terms, we need to apply properties of equalities here. So we will apply first subtraction property of equality, since there are two variable x at the left and the right. So we will subtract x both sides. So for x minus x, that will be 3x plus 10. And x minus x is 0. So the remaining number here at the right side is 1. And then we will subtract 10 both sides again. So we have 3x plus 10 minus 10 is 3x at the left side of the equation. 1 minus 10 is negative 9. And our aim here is to get the value of x there. And since 3 is together with that, so we need to divide 3 both sides of the equation. The division property of equality. So we have the x divided by 3 is x, and negative 9 divided by 3 is negative. Therefore, the missing number here is negative 3. Let's try to check. 4 times negative 3 is negative 12, plus 10 is negative 2, and negative plus 1 also is negative 2. Therefore, our solution here is correct. With example 2, the logarithm of x squared minus 14 to the base 8 is equal to logarithm of 5x to the base 8. Since the bases are both 8, we simply set the arguments equal. So we have x squared minus 14 is equal to 5x. And we will apply the subtraction property of equality here. We will subtract 5x both sides. So x squared minus 14 minus 5x is equal to 5x minus 5x. And we have here at the left side, we have x squared minus 5x minus 14 is equal to 0. And we need to factor that. So we have the factor of x, or x in x, and the factor of negative 14 is negative 7 and positive 2. We will not use negative, and we will not use positive 7 and negative 2 because the middle term here is negative 5. So we will use negative 7 and positive 2. So if we will add them, negative 7 plus 2, that is negative 5. And we can get the coefficient here, the middle term. So the factors are x minus 7 and x plus 2. And we have two value of x here. So x minus 7 is equal to 0, and x minus 7 plus 7 is x, and 0 plus 7 is 7. Therefore, x is 7 here, and x plus 2 minus 2 is equal to 0 minus 2. X is equal to negative 2. Now, we have two solutions here, 7 and negative 2. If we take a closer look at the definition of a logarithm, however, we will see that not only must be positive bases, but also we see that the arguments must be positive as well. Therefore, negative 2 is not a solution. And we will take 7 as the solution for this. So let's end this lesson by taking a closer look at this example. Our final concern then is to determine why logarithms like the one below are undefined. So we have logarithm of -8 to the base 2. Can anyone give us an explanation? Or can you give the logarithm of this? Okay. The logarithm of -8 to the base 2 is undefined. Why? And one easy explanation is to simply write this logarithmic form in exponential form. We'll then see why a negative value is not permitted. So we have logarithm of -8 to the base 2 is equal to y. And we have to write it in exponential form. Again, logarithms are exponents, and our base here is 2. Our logarithm is y, so 2 to the power of y is equal to -8. The question is, what power of 2 would give us -8? As we know that 2 cubed is +8, and 2 to the power of -8 is also 1/8. So how can we get -8 here? So hence the expressions of this side are undefined because we cannot get the value of it. Now we have characteristics about the graph of an exponential function. We have f of x is equal to a to the power of x, where a is greater than 1. Okay, number 1, domain is all real numbers. Number 2, range is positive real numbers. Number 3, there are no x-intercepts because there is no x value that you can put in the function to make it equals to 0. Number 4, the y-intercept is always 0 and 1 because a to the power of 0 is equal to 1. Number 5, the graph is always increasing. Number 6, the x-axis where y is equal to 0 is a horizontal asymptote for x to x approaches to negative infinity. Next is characteristics about the graph of a logarithmic function. F of x is equal to the logarithm of x to the base a, where a is greater than 1. Number 1, range is all real numbers. Number 2, domain is positive real numbers. Number 3, there are no y-intercepts. Number 4, x-intercept is always 1, 0. The x and y is right places. And number 5, the graph is always increasing. Number 6, the y-axis where x is equal to 0 is a vertical asymptote. So those are the characteristics about the graph of an exponential function and the graph of a logarithmic function. Okay, so you take a look at this graph. So the first one is an example of an exponential graph, and the other one, we have the logarithmic graph. And the graphs of inverse functions are reflected on y is equal to x. So they're inverses with each other. And the graphs of inverse functions are reflected about the line y equals x. Okay, here also we have transformation functions applied to logarithmic functions, just like they apply to all other functions. So kindly take a look of this. We have f of x is equal to 2 plus the logarithm of x to base 10. So the graph here, 2. And then the second graph is f of x is equal to logarithm of x plus 1 to the base 10 and left 1. And here we have reflect about x-axis. First graph, ang graph of f of x is equal to logarithm of x to the base 10. And here, the negative logarithm of x to the base 10. It reflects about x-axis. So, remember also our natural base e. We can use that base on a logarithm also. Logarithm of 2.7182828, the base e is equal to 1. So what exponent we put in a to get 2.7182828? So we have the natural logarithm 2.7182828 is equal to 1. Since the logarithm with this base occurs in nature frequently, it is called the natural logarithm and is abbreviated LN, and you can find it in your scientific calculator. When your calculator knows how to find natural logarithms, locate the LN button in your calculator and notice that it is the same key that has e to the power x above it. The calculator lists functions and inverses using the same key, but one of them needing the second or inverse button. Another commonly used base is base 10. A logarithm to this base is called a common logarithm. And since it is common, if we don't write in the base in a logarithm, it is understood to be base 10. Or if we cannot see any subscript of the LOG, which is the symbol for logarithm, that is understood as base 10. And that is a common logarithm. So we have logarithm of 100 is equal to 2. Then what exponent do you put on 10 to get 100? So that is base 10, diba? 10 squared is equal to 100. Next is the logarithm of 1 over 1000 is equal to negative 3. And what exponent do you put in 10 to get 1 over 1000? So 10 to the power of negative 3 is equal to 1 over 1000. So this common logarithm is used for things like the Richter scale, for earthquakes, and decibels for sound. So those are the real-life application for common logarithms, which is base 10. So if you can see logarithmic equations like this, just remember that base is 10 and that's common logarithms. Your calculator knows how to find common logarithms, so locate the LOG button on your calculator and notice that it is the same key that has 10 to the power x above it. Again, the calculator lists functions and inverses using the same key, but one of them needing second or inverse button. Okay. The secret to solving logarithmic equations is to provide the logarithmic equation in exponential form and then solve. So we have the logarithm of 2x plus 1 to the base 2 is equal to 3. Then convert this to exponential form so that we can get the value of x there. That is beside 2. What is that unknown number? So we have 2 cubed is equal to 2x plus 1 because the base 2, and as we know that the logarithm is the exponent. So 2 cubed is equal to 2x plus 1. And we have here 8 is equal to 2x plus 1 because 2 cubed is equal to 8. Because 2 times 2 times 2 is 8. And we will subtract on both sides of the equation. That subtraction property of equality. Whatever number you have to subtract at the left side is the same number you are going to subtract at the right side. So 8 minus 1 is 7 and 2x plus 1 minus 1 is 2x. Since 2 is together with x, so we need to divide to both sides, and that's division property of equality. So 7 over 2 is equal to 2x over 2. And x is equal to 7 over 2. And to check, we have the logarithm of 2 times 7 over 2 plus 1 to the base is equal to 3. And if we will apply the cancellation here, so we will cancel 2, so we have 7. So 7 plus 1 is 8. And the logarithm of 8 to the base 2 is equal to 3. And this is true since 2 cubed is equal to 8. Therefore, our x here is correct. So our IFL here, like logarithm, wherein it is a reverse of exponential function, we can make reverse of things we done that we're not good. We have always given the chance to correct our wrongdoings, and that it is always on our decision to choose what's best for us. Also, logarithms reminds that God is really an awesome God, for He knows everything on us, like the strands of our hair, the sands, and all other organisms we're in. We ourselves can't count it. So, good day, everyone. I hope you learned something today.